Happy Thursday. Wrote your final. It was fun. I loved it. Make sure you're here on Tuesday because I'm going to hand it out on Tuesday. And then you'll have to come in sometime during the final period to turn it into me. There's my workaround to me requiring you to be here during the final. Second. Yep. 5 to 7. I'll be in this room.
That should be good. Did you sure you
Good. The question is, do I want to?
and you please repeat it?
Well, since you asked so nicely, I only charge you $500,000 instead of $1 million. I'm handing out the final on Tuesday. And you have to turn it in during the final period. And I had fun writing it.
Yeah, we'll put the final.
Yep.
Good.
That'll just be the standard take home on Teams. We have to finish up parametric equations. Position of a particle moves along a curve that is given. What are the coordinates? Well, where the coordinates are measured in feet, t, and seconds. I want to do three things. Find time. Find the time rate of change of x when t is pi over 3. Time rate of change of y when t is 5 pi over 3. And time rate of change of the angle of inclination of the tangent line when t is 2 pi over 3. Bless you. And for part A,
So what's the difference between the time rate of change of x and the rate of change of x?
just specifying that this is rate of change with respect to time. That's it. Because you could theoretically do rate of change with respect to something else. Here it wouldn't make much sense, but you could. So the problem just specified time. Right, didn't need to. All right, x of t, 2 minus 3 cosine of t. So x dot just be negative 3 sine t, right? Evaluated at pi over 3. What's sine of pi over 3? Oh, I'm sorry, that shouldn't be negative 3 sine, right? Because already minus 3 cosine, that should just be positive 3 sine. Sine of pi over 3. And units, feet per second. Right, well, what this means is at the point, or at the time, pi over 3, our horizontal distance is changing at a rate of 3 root 3 over 2 feet per second. Y of t is 3 plus 2 sine makes y dot 2 cosine. Cosine of 5 pi over 3. Bless you. Close. Check your quadrant. It's positive 1. We're in quadrant 4. So 1 foot per second. Angle of inclination of the tangent line. No. Tangent of theta is gonna be the slope of the line. And we know dy dx, y dot over x dot. Theta would then just be the inverse tangent of 2/3 cotangent of t. Nope, I don't want that, not yet anyway. Because they wanted rate of change of this angle. Ooh, yeah, that's fun. So theta dot. That down. Derivative of the inverse tangent of u. Derivative of u over 1 plus u squared. We need the derivative of 2/3 cotangent, which is what? It's the derivative of cotangent. Bless you. We might be able to simplify that, but I don't care because I'm going to be evaluating it. Evaluate that at 2 pi over 3. I'll give myself enough. The cosecant of 2 pi over 3.
over root 3.
So we're going to square that. Cotangent of 2 pi over 3.
Over 3.
Nope. And I'm going to square that. Get 1/3. So 1 plus 4 over 27. 31 over 27. So that become 3, 8 times 3, 24. Make it 24 over 31. Units. For the units. Radians per second. Right. Or if you really want to be accurate, just inverse seconds, because radians are unitless. It's more of a placeholder than anything. But per second just doesn't sound right. That's why we usually write rads per second. Arc length of a parametric curve. Integral from T0 to T1 of the square root of x dot squared plus y dot squared dt. And in calculus 3, we're going to write that in an even nicer form. Arc length of our curve would be the integral from 0 to 4, square root. Four t squared plus 9t to the 4th dt. We can factor out a t squared from under the radical. Square root of t squared over this interval is just positive t. Right? Because t is positive on 0 to 4. Derivative of 4 plus 9t squared is 18t. So I'm going to wind up multiplying by 1/18. One divided by 3/2. Then our function to the 3/2 power. That will be evaluated from 0 to 4. One over 27 times. Okay, when t is 4, we're going to get 9 times 16. 54. 230. What am I saying? 230. 134. No,
144.
144. And then plus 4, 148. To the 3/2. This one's going to be easy. When t is 0, let's get 4 to the 3/2. One 148 to the 3/2 would be 148 times the square root of 148. 148 is divisible by 4. One 148 over 4. $37. And then 4 to the 3/2 is 8. It was actually at 8 common in 296 and 8. $37 root 37 minus 1 is the result. There's the arc length. Yes. I did change a variable in my head. So I let u be 4 plus 9t squared.
Oh.
Derivative is 18t, so I need a 1/18th. Many of the curves are going to give you hideous integrals. In fact, most of the curves are probably going to give you integrals that cannot be done analytically. You'll have to do them numerically. That's just the nature of arc length. Chances are, though, the curves that you're going to be given on like a test or a quiz are going to be fairly simple integrals. Right? They're chosen in such a way that what's under the square root simplifies nicely. Much like when we looked at arc length of y equals f of x, the ones that you got for the most part would simplify down nicely and be doable. If it's not possible to do by hand or analytically, I will tell you to use a numerical technique, and I'll tell you how accurate I want it. Probably going to be Simpson's rule. Length of an arch of the cycloid of theta minus sine of theta, 1 minus cosine of theta. All right, we have parameterization of our curve. What is our interval?
Thing 0 to 2.
You don't sound too confident.
Then after that, we gotta keep repeating them.
Let's make this interesting. This is new Las Vegas, except instead of money, it's grades. How much of your grade would you be willing to gamble on that answer? Oh, that's not a confident answer then. That's a real shame. I could be a typical math person and make it more of, you're in a dark alleyway and you're asked what the interval is, and the person says if you guess right, you're going to get $1 million. If you guess wrong, you're going to get shot. Would you take that risk on your answer? Well, you just won $1 million. Well, actually less than $1 million because Uncle Sam wants his cut. Do you remember from Tuesday, one of the parametric equations that we plotted was this, and I told you it was a cycloid. And if you remember, we did 3 intervals, 0 to 2 pi, 0 to 3 pi, and 0 to 4 pi. 0 to 2 pi is 1 arch. 4 pi would give you 2 arches. Actually, we could have also done 2 pi to 4 pi. Any interval of length 2 pi would give you 1 full arch. Derivative of theta minus sine of theta with respect to theta is what? Derivative of 1 minus cosine with respect to theta. And expand it out. It simplifies down to integral 0 to 2 pi of the square root of 2 minus 2 cosine of theta. Never logged out of this. Oops. So this does have an analytic solution. Oh. God, I'm stupid. Half angle identity on sine. And then square it. So 1 minus cosine would be 2 sine squared of theta over 2. And so we just factor out a 2 first, apply the identity, and then from there it's a simple matter to find the analytic solution. The answer is 8. Questions on parametric equations? Surface area is discussed in the lecture video. It is even more hideous than this. This is why we invented the CAS. Final topic of the semester, polar coordinates. Of course, you're gonna make me reboot, yeah. Polar points. Ordered pair of r theta Right, so call the point P. R is the distance from the origin to the point. Theta is the angle that the line segment OP makes with the positive x-axis.
Assuming O is the origin.
Yes. Think your text allows R to be negative, which for me doesn't make any sense because R is measuring a distance, and distance is not negative. So I'm never going to let R be negative. If R theta is the polar representation of point P, is it the only polar representation? In other words, are polar points unique? You're saying yes, it's the only point? You say no. Perfect, I have opposing answers. Guess I'll be a math person again. One of you is going to get shanked. Question is, which one? So I'll ask you, why do you say it's unique? Oh dear. Why do you say not unique?
Because it could be different points, it's not just one, it could be different points,
What do you mean different points?
there's more than one.
Right, but why? Why is there more than one? Technically, there's only one point. It's just, could there be different representations in polar for that point? Sorry, dude. You're getting shanked. Polar representation is not unique. If R theta's representation isn't R and theta plus 2 pi, theta plus 2 pi is essentially the same angle. So is theta minus 2 pi. So no, they're not unique. However, we typically restrict theta to be between 0 and 2 pi. So in that sense, then it would be unique. There'd only be one. That is the general acceptance. R, of course, non-negative, and theta will be an angle between 0 and 2 pi. We break with that in Calc 3. When you start to do polar integration. Actually, we might even do it a little bit here if we're integrating in polar. Right, because it might be more convenient to say, right, negative pi over 2 to pi over 2. instead of 0 to pi over 2, and then another integral for, what is it? 3 pi over 2 to 2 pi. Right, so I just write negative pi over 2 to pi over 2 instead. Now, here's the question. How are you going to convert from polar to rectangular? Rectangular is just also referred to as Cartesian. So that's the xy. Those are your conversions. Polar to rectangular. Derivation is in the video, but it's not too hard to see. Rectangular to polar. R squared is x squared plus y squared. Tangent of theta is y over x. Would we be able to say that r is the square root of x squared plus y squared? Why no? Right, but remember, what is r representing? A distance. Can distance be negative? So yes, you could just do r is the square root of x squared plus y squared. But again, by convention, it is acceptable to have a negative r. I don't like it. I will never use it. Would we be able to say theta is the inverse tangent of y over x?
That restrict you to only half the circle.
You cannot. The range of the inverse tangent is minus pi over 2 to pi over 2. Even if we ignore the custom of 0 to 2 pi, that still only gives you quadrant 4 and quadrant 1. You actually will have to look at the values for y and x to determine how to proceed to find theta. If y and x are in quadrant 1, you're done, right? Just take the inverse tangent, you're fine. If in quadrant 4, theoretically, you're done. You can just take the inverse tangent. Unless I specify theta has to be between 0 and 2 pi, then you have to add 2 pi to it. If you're in 2 or 3, you're going to have to add pi to the inverse tangent. And I do have an example of that, so I can show you. Oops, we just did that. I copied you. Convert 1-1 from rectangular to polar. Right, r squared is 1 squared plus 1 squared. That makes r the square root of 2. Tangent of theta is 1/1. Where are we located? So where is the point 1,1 located? Well, that's theta. I'm just asking right now, where's 1,1 located? Quadrant 1, so you can just take the inverse tangent and get pi over 4. Point in polar coordinates would be the point √2 pi over 4. Point -3, 0. R is going to be 3. That's fairly obvious. Tangent of theta is going to be 0/-3. True or false? Theta is the inverse tangent of 0. Why? Well, technically, the point's not in a quadrant. It's on an axis. The axes are not technically quadrants. Right, but you are right. It's not the inverse tangent of 0. You have to add pi to it. Right. There's our point. There's the point that the inverse tangent is going to give us. Call that P prime. So how do you get from here to there? Just a straight line. So you add pi. That's why. What is the inverse tangent of 0? I just gave it away. It's 0. So theta's pi. By the way, if you just type into your calculator inverse tangent of 0 over -3, you're going to get 0. It's a point, but it's not in a quadrant. It's on the x-axis, specifically the negative x-axis, right? Quadrants are only between the axes, right? So this would be 1, 2, 3, and 4. On the actual axes themselves, you're not in a quadrant, right? You're not in here. You're not in 2 nor 3. They have a name for that. I just forget what that's called. I just say it's on an axis. Specifically, it's on the negative x-axis.
So yeah, it's on negative x-axis.
It's not in any quadrant.
Yeah, you add
So you'd add pi.
then the other cases again, like, so there's one you add pi, one you don't, you need to add in between this.
If the inverse tangent's gonna give you the location of your point. So if you're anywhere over here, keep in mind, if you're actually on the y-axis, you're dividing by 0. So you can't even do the inverse tangent there. You'd have to just realize, oh, I'm on the negative y-axis, so my angle is 3 pi over 2. Right, you could have also just done that here, right? You could have just observed that and gone, oh, look, -3, 0, that's the negative x-axis, clearly the angle's pi. So there's our point in polar. Again, using the convention of 0 to 2 pi.
So you wouldn't usually see.
Sometimes it's obvious. So like here, I can clearly tell it's not polar, because if it was, R would be negative, which we can't have. So I know it has to be rectangular, otherwise there would be no way to know, right? Is that 1, 1 is in X is 1, Y is 1, or is that 1, 1 is in R is 1, theta is 1? Because you can't have theta equal 1 radian. You don't know unless you're told. So you will always be told. Right? Either by saying convert the rectangular point blah to polar, or convert the point xy equals 1, 1. Right? So in some form, you're going to be told. I could also just say convert it to polar, in which case it's obviously rectangular, right? Not so obvious in Calc 3 when you have 2 other coordinate systems, cylindrical and spherical. They're just as easy as this. You just have that third component to deal with now instead of the 2. So it's literally just an extension of what we're doing right now. Oh, that's the one I just did. Lucky for you, I'm not teaching Calc 3 next semester, as of right now. That could change, and then you get stuck with me. Considering Calc 3 is my favorite of the 3, you'd be really screwed. Root 3, -1. And so R squared, root 3 squared plus -1 squared, we get 4. That means R has to be 2. Tangent of theta is -1 over √3. Would that be true? And so I saw a yes. Who's gonna be devil's advocate and say no? Nobody. All right, we have a devil's advocate. You're both correct. It depends on, do I want it between 0 and 2 pi or not? Right, because that angle's -pi/6, which is valid. If I want from 0 to 2 pi, then you just have to add 2 pi to it to get 11 pi/6. But I will specify what I want. Otherwise, I would accept either answer. So the point in polar would be 2 11 pi/6, 2 -pi/6, either one. Or again, just keep adding, subtracting 2 pi. Right, add or subtract multiples of 2 pi, and it would still be acceptable. The point -3, 4. -3 squared plus 4 squared is 25, means R is 5. Tangent of theta would be 0. I'm sorry, 4 over -3. Would this be true? Have to add pi. Right, because our point is located in the second quadrant. The inverse tangent is going to give us an angle in the fourth quadrant. What is the inverse tangent of -4/3? It's a trick question. It's the inverse tangent of -4/3. Doesn't have an exact form outside of that. So just leave it. So there'd be your polar point. I noticed that we always did it in radians. That is implied in the definition that theta is measured in radians. I've never seen a polar point defined with theta in degrees. Ah, where was this all semester? This is easy. Like, oh, we saved the easiest for last. What if I want to describe a set of points instead of just a single point? Right, because remember, that's what a relation is. It's a set of points. It's a description for a set of points. X squared plus y squared equals 4. We write that as a polar equation. Now, again, standard convention is when you write something as a polar equation, you write it as r equals f of theta, if possible. Well, x squared plus y squared, isn't that r squared? Which should make r equal to 2. X squared plus y squared equals 4 can be described, that entire set can be described as r equals 2. That is a circle of radius 2. Right. So this is the set of all points in polar such that the distance from the origin is 2, which is clearly a circle of radius 2. X squared minus y squared is equal to 1. Now, wouldn't x be r cosine theta? And then, of course, y is r sine theta. Right now, that's what we have. Can factor out an r squared. Now, you could just divide both sides by cosine squared minus sine squared. You'd have 1 over cosine squared minus sine squared is equal to r squared. That just looks hideous. What is the identity for cosine squared minus sine squared? There is one. This is where a nice understanding of the trig identities comes in handy.
1 minus 2 sine squared.
Technically, yes, but that still isn't as nice. Cosine of 2 theta. It's the double angle identity for cosine. Which of course is also equal to 1 minus 2 sine squared or 2 cosine squared minus 1. Right, they're all double angle identity for cosine. Which would make r squared equal to the secant of 2 theta. Would we be able to take these square roots? What about secant of 2 theta? Technically, it is not. However, this has an implied domain. You can't have thetas where secant is negative because then you'd be saying r squared is a negative value, which is nonsense. So I'm gonna go ahead and take the square root. Because it's already implied that theta is not gonna be anything that makes secant of 2 theta negative. X squared over 9 plus y squared over 4 is equal to 1. This is an ellipse with a horizontal major axis. Semi-major is 9, semi-minor, I'm sorry, semi-major is 3, semi-minor is 2. I'm just going to go ahead and get rid of the fractions before continuing on. Bummer. And we could write either sine squared or cosine squared in terms of the other. Would that actually? that be beneficial? Mm. That'd be what, 4r² plus 5r² sine squared is equal to 36. Does that help? I guess it just makes it look nicer. This, of course, means that this is always going to be positive. You have a positive plus positive, and then under a positive. I mean, if you wanted to, you could also write it this way. That actually doesn't look as hideous as I was expecting it to look. That actually looks quite nice. You could have also done, would have been 6 over the square root of 5 minus 4 cosine squared. Or if you decide to replace sine squared with 1 minus cosine squared instead. Which will still always give you a positive value because cosine is between -1 and 1. So cosine squared is less than 1. 1 or less, I should say. So you'd have 5 minus 4 times something, 1 or less, positive. Awesome. And now we end with some cool problems. Going to plot the following functions. Now, there are 2 ways you can go about doing this. You could first write this in rectangular and then plot it. If you have the TI Nspire CAS, you do not need to worry about that. Entry mode. Number 5 gives you polar. All right, so you just have to write your f of theta. 1 minus 2 sine theta over 2. Get rid of this label. Let's go ahead and just No rude jokes. Of course, we also have Mathematica, which is my preferred. Polar plot. Allows you to plot functions of the form R equals f of theta. I'm going to go the default 0 to 2 pi. I do not remember how this is going to look. Perfect. Notice it's giving it on the x, y plane. There is a setting. Get what it is now, though. To turn off the XY axes and turn on the polar axes. So I could. Oh dear, and that came off hideous. It doesn't want to do the radial. I know there's a way I can get it to do the radial and not cut these bloody things off. There we go. That's actually what I wanted. And then, of course, I can still turn on. This is the true polar plane. Right. The rays represent the different R's. And of course, I'm sorry, no. The circles represent the different R's. The rays represent the different angles. But in most circumstances, that does not tell us anything. So you will typically just see polar curves plotted on the XY plane. And that's how I'm going to leave them. I have to remember we're not done at 45, we're done at 40, so sadly we're out of time. There are 2 more plots to look at, so we'll do that Tuesday. And then, of course, with same thing when we did parametric, we see a polar curve, we want to go, what's the slope at a point? What's the length of that polar curve? What's the area of that inner region? So we'll do calculus on polar curves as well. Then there's one more quiz that will be done on Tuesday, and the last homework assignment was just assigned today. All right, that means test 4 will also be assigned next time. Have a wonderful weekend. Might actually just. You too.